In the previous lecture, we saw the importance of features as predictive data, ending with a feature's big picture guide. In this lecture, we will walk through this map, exploring each of its areas in detail. We will delve deeper into feature selection, including how to apply exploratory data analysis, or EDA, feature engineering, feature selection, and feature importance. Let's see again the feature's big picture guide, and let's look at the key aspects of predictive data. We must understand feature engineering, feature selection, feature importance, and the initial data and EDA. Original data. We start by collecting and loading original data from various sources. It's essential to ensure data accuracy, completeness, and usability. Handle missing values, inconsistencies, and errors carefully. In technical analysis, we typically retrieve historical data, including open, high, low, close, and volume. We will check for data quality issues such as missing values, outliers, and duplicates. Once we have reliable data, we must understand it. The model specification will require understanding the data, so we should explore it. This is what we call exploratory data analysis. At EDA, we will perform descriptive statistics to understand the data distribution, visualize data to identify patterns and trends, and look for anomalies, since nobody wants to train their models with anomalies. In the image, we can see a typical data price table retrieved for Applied Materials Company. Understand relationships between variables means using correlation matrices, scatter plots, and other visualizations, and also formulate hypotheses and identify potential features for further engineering. Feature engineering. The original data is not enough. We need to calculate technical indicators and create new features from the original data. This involves transforming raw data into meaningful features to improve the performance of machine learning models. Techniques include calculating moving averages, relative strength index, or RSI, and other domain-specific indicators. A couple of details. First, we go from 755 rows to 722. This is because when calculating some indicators, there are dates where we don't have enough data, and we remove those from our input. For example, if we use a 21-session moving average, the first 20 days won't have enough data to calculate it, so we will eliminate those days. Second, additionally, we have already created the column we want to predict, the label or target, in this case, whether the price will go up or down tomorrow. We have data for all cases except the last one, since we don't know what will happen the next day. In both academic studies and numerous practical cases, we find an imbalance due to the overabundance of the use of technical indicators compared to other signals. Technical indicators are easy to calculate compared to, for example, scanning for chart pattern. However, let's consider that feature engineering is a very broad field, so a column or feature could be categorical, indicating the absence or presence of a candlestick pattern, chart patterns, Ichimoku scenarios, and so on. Additionally, among the features, we could have other types of feature engineering, such as market sentiment, which is an indicator that does not derive from price but from the sentiment present in news and social media posts about a company. Now, the columns with the features and even the labels can contain non-numeric data, but machine learning works with numbers, so we need to convert everything to numbers. This is part of the transformation or feature engineering process. Categorical data, with categories such as up and down or good, neutral, and bad, need to be transformed into numbers. This task is called encoding. Label encoding is easy. It only needs to convert categorical data into numerical values by assigning a unique integer to each category. For example, true is 1 and false is 0. Machine learning algorithms often interpret numerical values with an inherent order, meaning the algorithms can consider some numbers to be greater than others. Ordinal encoding is used with ordinal categories that have an intrinsic order. For example, terrible is 1, bad is 2, neutral is 3, good is 4, and excellent is 5. Because in the categories, that is the real order, and neutral is between bad and good, the same as 3 is between 2 and 4. But what happens when there is no intrinsic order? If we assign a 1 to shooting stars and a 2 to dark cloud covers, the algorithm will incorrectly conclude that dark cloud covers are more or greater than shooting stars. This can lead to misleading results because the numerical values introduce a false sense of order and magnitude. 1. Hot encoding is a method to convert categorical data into binary columns, where each category gets its own column with a 1 for its presence and 0 for its absence. For each category, we need a column where we will place 1 or 0. For example, no pattern will show 1 if there is no pattern and 0 if there is a pattern. Shooting star pattern will show a 0 if there is no shooting star pattern and 1 if there is. We do the same with all the categories. Furthermore, what if a column has categories such as the street where a company's headquarters is located? If there are 3,000 streets, we would have to create 3,000 new features, greatly increasing the size of the dataset. This can be managed using techniques like target encoding, frequency encoding, or, in the case of deep learning, embedding layers. Now that all the data are numerical data, we must scale them to ensure uniform contribution from all features. Many machine learning algorithms perform better when features are on the same scale, ensuring fair contribution and also faster convergence. There are several ways to scale data, one of the most common being normalization. Normalization, or min-max scaling, scales the data to a fixed range, typically 0 to 1. This is useful when you want to ensure that all features have the same scale. Proper scaling can significantly improve the performance of the model and speed up the convergence of the algorithm. Feature selection methods. Apply techniques to reduce dimensionality and eliminate irrelevant or redundant features. This step aims to enhance model performance and interpretability by selecting the most informative feature. These methods include generic techniques like filters, wrapper methods, and embedded approaches. Filtering methods are the simplest part of feature selection. These methods include elimination of constant, quasi-constant, correlated, or low-variance features. For example, if we have introduced market sentiment as a feature, but the column always appears with neutral, it is an irrelevant feature that will only add noise to the model's training. In this case, no engulfing pattern was found at all, so we delete this column or feature. Also, if we have only found one dark cloud cover, the model will not be able to learn the effects of this pattern, so we can also delete this feature. Additionally, many times we work with correlated data. In this case, rock and momentum are extremely highly correlated, so they will give the same information and result in redundancy. Wrapper methods use a predictive model to evaluate and select combinations of features. This involves iteratively adding or removing features and evaluating the model's performance. It is like cooking a dish by removing some ingredients and keeping others, then tasting the final result to understand the contribution of each ingredient to the overall flavor. Embedded methods use techniques that are built into the model training process to determine which features are important. These methods simultaneously select features while the model is being trained. Feature importance means evaluating the importance of selected features using methods like random forest, linear regression, and others. This step involves assessing which features have the most significant impact on the model's predictions. Feature importance can be determined through various methods. In conclusion, handling features involves a series of steps starting from the original data and EDA, followed by feature engineering, selection, and evaluating feature importance. These steps are crucial for improving the performance and interpretability of machine learning models.